We have shown so far that all of the linear properties of motion can be translated into circular motion. We have looked at distance. For a circle, this is the amount an object has travelled around a circle, either in standard units of distance, metre, etc., or as angles around the circle, degrees or radians. We have looked at velocity and shown how we can work this out using the linear speed equation of distance divided by time and assigning a direction to the motion. We have also looked at the rate of travelling through angles with a circle and defined an equation for angular speed. What we have not done so far is defined acceleration in a circular path. If the linear principles still hold true, then acceleration in a circle is merely speed divided by time. The big question becomes, which direction? So far we have not talked much about direction. When we are looking at tangential velocities, the direction comes about from working them out from the tangent the velocity follows. When working out the angular speed, we do not need to worry about direction, as speed is a scalar property. For acceleration, though, we do need to consider direction. Newton's second law plays a key role in determining the direction of the acceleration in circular motion. If you observe an object circling about the centre of a circle, you will see that the direction relative to the orbiting system is constantly changing. An object taking a circular path, by definition, changes its direction constantly. The rate at which the object changes its direction is determined by the rate of curvature of the circle. The smaller the circle, the higher the rate of curvature for that circle, and so the more often an object will change direction. The bigger the circle, the bigger the radius, and so the slower the rate of curvature and change in direction. We can see then that the rate of change of direction is inversely proportional to the radius of the circle. If the speed is kept the same around the circle, then we can infer that the rate of change of direction, and so acceleration, is inversely proportional to the size of the circle, and so the radius. This doesn't tell us the overall direction of the acceleration, though. It just gives us an idea of how radius affects the magnitude of the acceleration. Newton's first law says that a force is required to change direction. Newton's second law tells us that whatever the force is, the acceleration points to it. So, if we can see which direction a force is pointing, we can determine which way the acceleration is acting on an object. For objects thrown in a gravitational field, the acceleration works towards the centre of that gravity. For an orbiting satellite, that direction is to the centre of the planet the satellite orbits. For a bucket on a string, the centripetal acceleration is to the centre of the circle. In all circular motion situations, the centripetal force is the force keeping the object in the circle. The centripetal force always pulls the object to the centre of a circle, and so the acceleration of an object undergoing circular motion must also be to the centre of a circle. Centripetal acceleration is always pointing to the centre of the circle. Its magnitude is linked to the radius of the circle inversely. What is left to determine is how the tangential velocity and angular speed affect this centripetal acceleration.